Thank you for joining this lesson. We're going to handle physics paper 1, that is the quantity of heat. Remember to subscribe and to share this link with your friends. Let me post my content now. Continue following. You can comment so that you may know where you are watching from and whether you're getting us clear. So let us know whether you are getting us well from wherever you are. Yeah, so on quantity of heat, I will start by defining a few terms, and that will enable you to be conversant with the whole topic. Quantity of heat. So there are some terms which we are going to define, other terms conflict, but by the time we'll be finishing up with this lesson, you'll be able to distinguish everything. Therefore, let me start by defining heat itself. And generally, heat is a form of energy that flows from one body to another due to temperature difference. We know very well from Form 1 physics on heat transfer that heat transfer can happen if two bodies are placed together and they are not at what we call thermal equilibrium. That is, a body is at a temperature above another one or below another one, then heat has to flow from one body, that is the one which is at a higher temperature, to the body which is at a low temperature. So generally, heat flows from a body to the other. There are factors which determine how heat flows. That is discussed in book 1 physics. Allow me clear some differences between heat and temperature, because some people confuse temperature and heat. These are two different quantities. Heat is a form of energy that flows from one body to another due to temperature difference, whereas whatever we call temperature is the degree of hotness or coldness of a body or even of a place that can be measured on a given scale. It can be the Kelvin scale, it can be the degrees Celsius scale. Other differences include the SI units of recording each of these quantities, and that is heat energy is recorded as a form of energy. It is recorded in joules, just like any other form of energy, but temperature is recorded in Kelvin, though Kelvin can also be converted into the degrees Celsius scale, rather the centigrade. So allow me now start handling what we call heat capacity. Heat capacity refers to the quantity of heat energy or the amount of heat energy required to raise the temperature of a given mass of a substance by 1 Kelvin. Instead of 1 Kelvin, a student can even say required to change the mass of a given substance by 1 unit. By 1 unit. Because when this raises by 1 degree Celsius, it will be the same as raising by 1 Kelvin, because the relationship between degrees Celsius and Kelvin is by addition or subtraction. That means changing in a unit can either be degrees Celsius or even in the Kelvin scale. So generally, heat capacity is abbreviated with a capital letter C. So we can now write mathematically and say that heat capacity is given by the quantity of heat given divided by change in temperature. So it can be heat energy absorbed, and it can also be heat energy released, or rather given out. Heat energy released, because a body might be cooling or losing heat. We will still talk about the heat capacity. So heat capacity, capital C, will be given by the amount of heat energy divided by the change in temperature, because we want the heat energy involving in changing the temperature by 1 unit. Therefore, we must know per unit temperature how much heat energy has been involved. And that is why we are saying it's the heat energy absorbed divided by the change in temperature, which might be an increase or even a decrease. From that, we can all agree that changing the subject of the formula now to Q, then it will be heat capacity times the change in temperature. So to get the amount of heat energy either absorbed or released, we can multiply the heat capacity of a substance by the change in temperature. Let us go to the SI unit of heat. This is the SI unit of heat capacity, not heat. The SI unit of heat capacity is joule per Kelvin. These are derived units because we are simply dividing energy, which is in joules, and change in temperature, whose SI unit is the Kelvin. Therefore, joule per Kelvin. That is why you can either write joule per Kelvin, capital K, or you write as it has been captured in the notes here, joule, then you take the K up with a negative power. It means the same. That is on indices now. All right. Different materials have different rates of heat absorption and therefore different heat capacities. What has not been captured is that different materials have different rates of releasing heat, or rather emitting heat. Emission of heat is directly proportional to absorption of heat. The faster a body can absorb heat energy, the faster it can release the same heat energy. So different materials or different substances will have different heat capacities. Different heat capacities. Yeah, allow me bring another quantity, which we call specific heat capacity. This time round, small letter c, and this is the quantity of heat energy required to raise the temperature of a unit mass of a substance by 1 Kelvin, or by 1 unit of heat. So we are talking about a unit mass now, not a given mass. Actually, the specific difference between specific heat capacity and heat capacity is that specific heat capacity is the amount of heat energy absorbed so that a unit mass of a substance may change its temperature by only 1 unit. I've said instead of 1 Kelvin, you can say by 1 unit, because changing by 1 degree Celsius will also mean changing by 1 Kelvin. Specific heat capacity, this is the heat energy absorbed divided by the mass of the substance multiplied by the change in temperature. In simpler terms, let me just tell you that what we call small letter c, this is a specific heat capacity. It's like now we are talking about heat capacity per unit mass. Heat capacity per unit mass. The heat capacity we were talking about now divided by mass. And when you multiply this by mass, we will talk about the heat capacity being equal to mass multiplied by specific heat capacity. Then now we can get back to the first equation, whereby we said it's good we remember that capital C, heat capacity, is equal to the amount of heat energy divided by change in temperature. So in this case, now we will talk of the amount of heat energy divided by change in temperature is equal to mass of a substance times the specific heat capacity. And now, again, we can make the energy absorbed or the energy released the subject in the formula. And that means we will land in a formula which says that quantity of heat either absorbed or released is equal to the mass of a substance times the specific heat capacity multiplied by the change in temperature. The SI unit of specific heat capacity is joule per kilogram per Kelvin. This Kelvin is supposed to be capital K. So allow me to write this. It's joules per kilogram, small letter K and G, per Kelvin, capital K. I said this can be captured as joule. Instead of dividing, we write kg raised to power -1. And per Kelvin, we also bring it up here and have a negative. But it should be noted that the SI unit of temperature is Kelvin, abbreviated capital K, not a small letter K. Specific heat capacity can also be expressed as heat capacity per unit mass. That is exactly what I had mentioned up there. So we can look at a few calculations now. We are talking of example 1. Calculate the quantity of heat required to raise the temperature of a metal block with a heat capacity of 460 joules per Kelvin from 15 degrees Celsius to 45 degrees Celsius. So to solve this question, you first of all have to understand the quantities provided. And the quantities provided in this case are, we have the initial temperature, we have the final temperature, then we have the heat capacity. So heat capacity is capital C. Heat capacity is 460 joules per Kelvin. Then we have initial temperature and final temperature. That means we can get the change in temperature for this metal block being heated from 45, okay, from 15 all the way to 45, there is a change of 30 units, which can either be degrees Celsius or the Kelvin, but we just say change by 30 units. Because if you convert to the Kelvin scale, whatever you will add to 15 to make it SI unit, you will also add the same value to 45 to make it SI units. And therefore, if the value being added is the same, that is 273, then when you subtract the two figures in the Kelvin scale, they will give you the same difference. So that is why we just take change in temperature regardless of the scale which has been used. So now we will say quantity of heat from the first formula is given by heat capacity of a substance times the change in temperature. In this case, we will have to multiply 460 by 30, and automatically we're going to get 13,800 joules of energy. So it's good to know that whenever you are calculating energy, you should record it in joules. Now there is a second example here, which says that a piece of copper of mass 60 grams and specific heat capacity 390 joules per kilogram per Kelvin. This should be kilograms, sorry. Joules per kilogram per Kelvin cools from 90 degrees Celsius to 40 degrees Celsius. Find the quantity of heat given out. As I had mentioned, I'm repeating that the quantity of heat energy given out, or rather released, is given by the same formula as to the heat energy absorbed by a given substance. So quantity of heat will be given by the mass of the substance times the specific heat capacity, small letter c, multiplied by the change in temperature. In this case, remember we should work with SI units. Therefore, mass of 60 grams should be converted to kilograms by dividing by 1,000, multiplied by specific heat capacity of 390 of this substance, times a change of temperature from 90 degrees cooling to 40 degrees Celsius will have a change of 50. And therefore, this will give us 1170 joules of energy. So that is the amount of heat energy which will be given out, or rather released to the surrounding. There is an example 3, says that we find the final temperature of a mass of water if a heater source rated 42 watts heats 50 grams of water from 20 degrees Celsius in 5 minutes. Specific heat capacity of water is 4200 joules per kilogram per Kelvin. Remember, now we are shifting from the heat energy which is being lost to the surrounding or being absorbed to heat energy being supplied by an electric heater, because we are given the rating of this electric heater. So we need to talk about the heat energy, which is electrical energy being converted to heat energy. And this is given by the power of the heater multiplied by the time. That is how we get electrical heat energy. In other cases, instead of being given power, remember electrical power can be given by VI. So instead of being given the power of a certain heater, you can be given the voltage and the current rating. And that will mean VI instead of power, then multiplied by time, will still be an alternative formula for the electrical heat energy being released or being supplied by the heater. So let us talk about now the quantity of heat which is going to be, because we are finding the final temperature and we have initial temperature, we will assume that there are no heat losses to the surrounding first. And if there are no heat losses to the surrounding, then all the heat energy supplied by the electrical heater, in this case, will be fully absorbed by water on the other side. Remember, the heat energy being supplied by heater will be given by power times time. The power is 42 watts. This will be multiplied by time. Time is supposed to be in SI units. Therefore, this heater is working for what we call 5 minutes. So it will be 5 by 60 to make it SI units. That is seconds, the SI unit of time. This is equal to power. We have power times time. This will be equal to now the heat energy absorbed by water. That means mass of the water, 50 grams. We divide by 1,000 to convert it to SI units, multiplied by 4200. That is the specific heat capacity of water. Multiplied by, we can multiply by change in temperature, which is not known. Change in temperature. Allow me use the standard abbreviation for temperature. Yeah, change in temperature. And that means we can divide 3 zeros here. Then we also cancel 5 and 5. We can also cancel 42 and 42. And this means we are going to have a change of temperature of 60 degrees Celsius. Therefore, when water was heated, it changed by 60 degrees. And initially, it was at 20. Because it is being heated, then it will find itself, or we will find this water from 20. After raising or changing by 60 due to heating, we will find water at 60 degrees, at 80 degrees Celsius. So that is now the new temperature, or rather the final temperature. Okay, alternatively, we can also say that 42 times 5 times 60 equals to 50 out of 1,000. This is alternatively. Let's check whether it will still work. Times 4200. Then now we multiply this by change in temperature from a known final temperature T. Then we have an initial temperature of 20. Yeah. So let us check whether final temperature will automatically take us to 80. So we again divide the 3 zeros, then by 5, and 42 cancels. Therefore, we will find ourselves talking about T minus 20 equals to 60. And to remain with T as the final temperature, now we will have to take 20 to the right-hand side where it gets added now, and we will have 80 degrees Celsius as the final temperature. So that is how we determine the final temperature in case it is asked. Thank you so much for continuing following. Remember to subscribe. Remember to invite friends as we continue with the live broadcast. Now we're going to look at how specific heat capacity of given substances can be determined. There are several methods. The first one being the method of mixtures. Then we have the method of electricity, or rather the electrical method of determining specific heat capacity of a substance. So let us look at the first method of determining specific heat capacity. Actually, I'll be a simple procedure. Then we will go to some examples. In this method, a relatively hot substance is mixed with a relatively cold substance. Heat energy is transferred from hot body to the cold body until thermal equilibrium is established. So specifically, we are mixing two substances here, a hotter one and a cooler one. When they are mixed, there must be heat transfer until thermal equilibrium is attained. And at that point now, we can have some calculations and say that the heat energy absorbed equals to the heat energy released by the other body. Then, in this case, again, one of the bodies should be having the unknown specific heat capacity, while the other will be having a known heat capacity. So that now we can relate mathematically and obtain their known specific heat capacity. So there are some precautions. Remember, let me analyze the diagram first before I give you a simple procedure. There is a metal block being heated in figure A. There is a metal block being heated there. There is over water. It is tied on a cotton thread. Yeah, there's a wire gauze there. So the metal block will be strongly heated. Then it is the one now which will be transferred to figure B. And on this side, we are having a material called a container called, or rather an apparatus called a calorimeter, which is containing water and a stirrer. Then there is a thermometer inserted there. There is a cardboard there. Yeah, then the metal block now will be inserted in this. Let us say that the precautions stated here are purposely to ensure that heat is not lost to the surrounding. For example, the calorimeter should be highly polished. We know very well highly polished substances will barely release heat to the surrounding. There is also another precaution that the calorimeter should be lagged. Lagging, you can see a lagging material here. Lagging is ensuring that you coat a substance by an insulating material. And this is to ensure that, again, heat energy is not lost to the surrounding. There is also the lid should be an insulator, again, to prevent heat from being lost to the surrounding. The procedure simply is, you're going to write this very fast, the method of mixtures. You heat strongly a metal block until it attains a certain temperature. Can have it as temperature 1. Then the mass of the metal block should be known. We can record it as also mass 1. So there is mass 1 and you are for the metal block, and you are heating the metal block until it attains a temperature. We can call it beta 1. Then at that point now, you have the other side, the mass of an empty calorimeter together with its star being determined. You record it as mass 2 because mass 1 is for the metal block. Then after that, you add some water to the calorimeter, at least water to an amount such that it can fully contain the metal block you have heated or rather the metal block can fully sink into the water. Therefore, you add some water to a standard level and you measure the new mass of the calorimeter together with its content. You record it as mass 3. Then now you quickly transfer the hot metal. That is after determining the initial temperature of water and calorimeter. Then you transfer quickly the metal block into the calorimeter and you start stirring. Stir with the thermometer until an equilibrium is attained, a thermal equilibrium. That is until a steady temperature is attained. You can record it as theta 3. The temperature 3 now, which is being attained. Temperature 2 is the temperature for water and calorimeter initially. Then temperature 1 is for the heated metal block. Now, in that whole process, the metal block is losing heat. I want you to understand that. The metal block is losing heat. But on the other side, there is water and calorimeter, which are absorbing the heat which has been lost by the metal block. The basic assumption of this experiment is that there are no heat losses to the surrounding. There are no heat losses to the surrounding. Therefore, mathematically, we will be able to generalize that all the heat energy lost by the metal block is equal to the heat energy absorbed by water, which is in the calorimeter, plus the heat energy gained by the calorimeter together with its stirrer. Together with its stirrer. Together with its stirrer. Therefore, there is this equation now. Heat lost by metal block equals to the heat gained by water in the calorimeter plus the heat gained by the calorimeter together with its stirrer. It's very important to note that in case we are determining specific heat capacity for a liquid, the same procedure is followed. That was what I've stated was determining specific heat capacity of a solid. But now for a liquid, we will follow the same procedure. A metal block will be heated strongly until it attains a certain temperature. Then a liquid now, not water, because the water has a non-specific heat capacity. That is why it has been used together with a calorimeter made of a material whose specific heat capacity is also known. So in the calorimeter now, for the case of liquid now, we will fill or we will add into the calorimeter now the liquid whose specific heat capacity is to be determined. And for this particular time, we will be using a metal block heated strongly and having a known specific heat capacity and mass. So we will have the same formula, and in the whole formula now, it is the specific heat capacity of the liquid now, which will not be known. So you find we are saying heat metal or heat lost by metal block equals to heat gained by. Now we will start talking about liquid. Heat lost by liquid plus heat gained by liquid plus heat gained by the calorimeter together with its stirrer. So I hope I'm understood that to determine the specific heat capacity of a liquid, we follow the same procedure. Let us talk of a mathematical example here. We're going actually to do 2 examples. 1, a lagged copper calorimeter. So the first thing to underline there is that you see the calorimeter is being lagged to ensure there are no heat losses to the surrounding. Again, it's made of copper. Therefore, the material making the calorimeter is copper. That means the specific heat capacity of copper should be given at some point, because that will be the specific heat capacity for the calorimeter. Of mass 0.75 kilograms, contains 0.9 kg of water at 20 degrees Celsius. A bolt of mass 0.8 kilograms is transferred from an oven at 400 degrees Celsius to the calorimeter, and a steady temperature of 50 degrees is attained or reached by the water after stirring. Calculate the specific heat capacity of the material of the mold. Specific heat capacity of copper is given as 400 joules per kilogram per Kelvin, and that of water is 4200 joules per kilogram per Kelvin. Let C be the specific heat capacity of the material making the mold. That is our unknown in this case. It's good we analyze the question first and say there is a water contained in a calorimeter and they are initially at 20. Then after transferring a hot bolt, which was at 400, there is a steady temperature of 50 being reached. That means water and calorimeter have raised from 20 degrees Celsius to 50. Whereas, mathematically, assuming that there are no heat losses to the surrounding, we will talk about the heat lost by the metal block will be equal to the heat absorbed by the calorimeter plus the heat gained by water. So water and calorimeter are gaining heat, whereas on the other side, the metal block, which is making the mold, is the one now losing heat energy. Therefore, heat lost by the metal block, we use its mass, 0.8 times unknown specific heat capacity, and the change in temperature will be 350. That is 400 minus 50 degrees. This is equal to the heat gained by calorimeter. Calorimeter is of mass 0.75. We multiply by specific heat capacity of the material making the calorimeter, that is copper, 400, times the change in temperature. From 20 to 50, we will have a change in temperature of 30. Then plus the heat gained by water. The calorimeter is containing 0.9 kilograms of water. We multiply this by 4200. Then we multiply by the change in temperature for water. So both water and temperature, both water and calorimeter are having the same temperature change from 20 to 50. So that is 30. When we compute that with a known C, we are going to get the specific heat capacity of the material making the mold is 437 joules per kilogram per Kelvin. Let us gauge another example, which I suppose will be involving now calculating the specific heat capacity of a liquid. We are told that a block of iron of mass 1.25 kg at 120 degrees Celsius was transferred to an aluminium calorimeter of mass 0.3 kg containing a liquid of mass 0.6 kg at 25 degrees Celsius. So we are having a metal block which is hot at 120. Then it's being transferred to a calorimeter made of aluminium, which is having a liquid, and they are at 25. That is to mean, as the metal block made of iron will be losing heat, then calorimeter, together with a certain liquid, will be gaining the same heat energy, with a specific assumption that there are no heat losses to the surrounding. Therefore, we are told that the metal block and calorimeter with its content eventually reached a common temperature of 50 degrees Celsius. Given the specific heat capacity of iron as 450 joules per kilogram per Kelvin, and that of aluminium as 900 joules per kilogram per Kelvin, calculate the specific heat capacity of the liquid. Calculate the specific heat capacity of the liquid. Let us look at the solution. Remember, there are no heat losses to the surrounding. Therefore, we are saying the heat energy lost by the iron block equals to heat energy gained by calorimeter plus heat energy gained by liquid. Therefore, we will talk of a mass of iron times specific heat capacity of iron times the change in temperature for iron. This will be a mass of calorimeter, specific heat capacity of calorimeter times change in temperature for the calorimeter. Then we add mass of the liquid times specific heat capacity of liquid times the change in temperature also of the liquid. Remember, in the whole equation, it is only specific heat capacity for this liquid, which is not known. Therefore, mass of metal block, specific heat capacity of the metal block times change in temperature from 120 until the thermal equilibrium. The thermal equilibrium is a very basic identity. You first of all have to understand this. From 120 to 50, we will have a change of 70 equals to a mass of the calorimeter 0.3 multiplied by 900 specific heat capacity of aluminium multiplied by change in temperature from 25 initial temperature to the thermal equilibrium of 50. There will be 25. Then plus the liquid now is having a mass of 0.6, then unknown specific heat capacity times 25 also the change in temperature. When you compute and follow through, you're going to get the specific heat capacity for this liquid as 2175 joules per kilogram per Kelvin. Let me wind up by discussing how to determine specific heat capacity of a given substance by the electrical method. In this method, electric heating coil supplies the heat which is absorbed by other substances, liquid and solids. We can have a setup here to see how the specific heat capacity of a metal solid can be determined using the electrical method. There is a setup here. There's a thermometer. There are two holes already on the metal block. Then one, there is electric heater inserted, as you can see. Then the other one, there is a thermometer which has been inserted on the other side. A precaution is to ensure that the metal block must be highly polished and heavily lagged to reduce heat losses by radiation to the surrounding. Then another precaution is that the two holes which have been made, one for the thermometer, the other one for the electric heater, must be oiled to improve thermal contact with the heater and the thermometer. Therefore, for the heat to be supplied well, because the heater will not be touching, will be just touching some parts, the oil will be heated and it will supply the heat uniformly to the metal block. So the simple procedure on the electrical method of determining specific heat capacity of substances is that you first of all make two holes on the metal block and you measure the mass of the metal block. Then you record, or you don't even record its initial temperature. Just make holes, oil them well, and record the mass for the metal block. Ensure that the metal block is shiny or polished and heavily lagged to ensure that there are no heat losses to the surrounding. Now insert your thermometer and insert the electric heater, which has been connected to an electric circuit. Then after that, adjust using the rheostat. This is the electric sample of a rheostat. That one we call it a rheostat. A rheostat is a variable resistor. Adjust using the rheostat until a steady current flows. When a steady current flows, you record the current and also you record the voltage, the voltmeter reading, and you record the initial temperature. That now will be the initial temperature from the thermometer for the metal block. Record the initial temperature. Then immediately start the stopwatch. There is a very crucial apparatus which has not been mentioned here. The stopwatch. So by the time a steady current is established using the rheostat, that is when you are supposed to record initial temperature for the metal block and simultaneously start the stopwatch. Then now you let heat to be supplied now at a constant current for some time, say time t. Then after you record some time interval t, you can observe the new temperature of the metal block, that is a delta 2. Then with that now, you are done with your procedure, you can move to the analysis of results. With an assumption that there are no heat losses to the surrounding, then we will argue that the heat energy supplied by the electrical heater is going to be fully absorbed on the other side by the metal block. So heat supplied by electrical heater, electrical energy is given by power times time, the electrical power times time. Therefore, the electrical power is VI times the time taken for the temperature to change. This will be equal to mass of the metal block times specific heat capacity of the metal block times the change in temperature for the metal block. Remember, after adjusting the current to a steady current, you recorded initial temperature, and after time t, you recorded the final temperature. Therefore, change in temperature for the metal block will be final temperature and the initial temperature subtracted. So that is how we get the change in temperature. We can have the procedure being repeated for liquids, only that now in this case, you are going to have the heat supplied by the electrical heater will be absorbed on the other side by the liquid in the calorimeter. For this case, we are having water, plus the heat also gained by the calorimeter itself, because the amount of heat energy absorbed by the calorimeter is not negligible. So we also had it there. And so we will argue that power times time, that is VIT, VI is power, then times time, equals to mass of the water, specific heat capacity of water times change in temperature for the water. Then we add mass of calorimeter, specific heat capacity of the calorimeter, multiplied by the change in temperature for the calorimeter. It should be noted that calorimeter and water, or the liquid in the calorimeter to be general, they will have the same change in temperature. It also should be noted that when we are talking about time, it should be in SI units. So in case time is provided in other units, be standby and keen enough to convert it to SI units, which are the seconds. Let's look at an example here. In an experiment to determine the specific heat capacity of water, an electric heater was used. If the voltmeter reading was 24 volts and that of ammeter 2.0 amperes, calculate the specific heat capacity of water if the temperature of a mass of 1.5 kg of water in a 0.4 kg copper calorimeter rose by 6 degrees Celsius after 13.5 minutes. Specific heat capacity of copper is 400 joules per kilogram per Kelvin. Remember, specific heat capacity of copper is provided because it is copper which is making the calorimeter. Allow me to say that in such an experiment now, the electrical energy being supplied by the heater will get absorbed by water and by calorimeter. Therefore, can we talk about heat energy supplied by the heater being equal to heat gained by calorimeter plus heat gained by water? Then now we will have voltage times current times change in temperature, times time, VIT. So this is V, this is I, and this is T. 13.5 minutes have been multiplied by 60 to make it SI units, which is the second. This is equal to 0.4 times 400 times 6. That is mass of the calorimeter, specific heat capacity of the material making the calorimeter, times change in temperature. We are told they rose by 6. Then for water, will be 1.5 times unknown specific heat capacity of water times 6, which is also the change in temperature for the water. C is the specific heat capacity of water. Therefore, you can now work out that and confirm that the specific heat capacity of water is equivalent to 4213. Remember to subscribe and to share with friends. Thank you.